Welcome to our webinar today. The topic today is stability analysis and torsional warping with 7 degrees of freedom in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, German and English webinars, etc. I will be the moderator today and I will answer your questions together with Sonja van Bloo.
Hello, my name is Oliver Metzkes, and here at Dlubal I'm working as a customer support and product engineer, mainly in the field of steel construction, and today I will present the webinar.
Okay, maybe an additional information. What we present today is also valid for RStab 9 because we are working with members. So then we can switch off our webcams that the attendees can see the full screen. Yeah, on the right side of your screen you can see a control panel and you can enter a question here. We will answer you. Yeah, in the case there are too many questions and you don't get an answer during the webinar, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, then I hand over the screen to Oliver. Oliver, it's your turn.
Okay, thank you, Andreas. So we will start the presentation. And first I want to present the content overview. So we are talking today first about the determination of the critical load factor using the structure stability add-on in RFEM. Then the second topic will be the consideration of the cross-section warping in the global calculation using this torsional warping add-on for 7 degrees of freedom. And we also want to talk about the lateral torsional buckling analysis according to Eurocode 3 using those both add-ons in the global calculation, so with 7 degrees of freedom, imperfections, and second order analysis. So the first thing that we want to look on is the structure stability add-on. So here's a short overview about the features of this add-on. So we can use the structure stability add-on to determine critical load factors for our structures and also calculate models consisting of member, shell, and solid elements. So in this webinar, I'm going to present members in the structure stability add-on because we also want to show the combination with the 7 degrees of freedom calculation. And I think shell elements and solid elements will be also part of another webinar in the future. Another feature of the structure stability add-on is also the nonlinear stability analysis. So we are using incremental loading to also calculate nonlinear systems in the structure stability add-on. There's also an option which will help us for the determination of a mode shape of an unstable model so that we can also find the cause of the instability. We will also look at this in the webinar today. And we can also have a graphical representation of the stability mode shape and use it as a basis for the determination of the imperfections. In the first example, I want to use a simple example in RFEM to show you the basics of the input for the structure stability add-on and also that we can see which results we will get from the calculation with the structure stability add-on. So I will switch to RFEM and we will have the first example. It's a very simple example in this case. So it's a simple steel frame. We have rigid frame edges and simple supports. And now we have here one loading condition. So we have vertical loading and a horizontal load. And we want to look at all the settings that are necessary to perform a stability analysis with this structure stability add-on for this example. So first, if you want to use the structure stability add-on, we need to activate it in the base data dialog. So I go into the edit model base data dialog, and then we have this tab for the add-ons where we can activate the add-on structure stability. You have probably noticed that in the main tab of the base data, we have chosen the model type 2D. So if we have chosen only this 2D model type, also structure stability analysis will also be performed in this 2D plane stress environment. So we will see in the first step only mode shapes for this 2D structure. Okay. So now I have activated this add-on, and we will see that in the navigator for the data, we have an additional stability analysis setting. So without the stability add-on, we don't have the setting, but now it's here with already two predefined stability analysis settings. If we open the first one by double-clicking on it, we see that in this stability analysis settings, we can set all the options that we want to consider for our stability analysis. So we have as an important choice the stability analysis type. So we have this linear eigenvalue method for determination of the critical load factor. And also, as I said, we also have this incremental method for calculating nonlinear systems. So in my example, I only want to use this standard eigenvalue method for the linear system, and I also don't want to change the other options for now. When we have our stability analysis setting, we can also assign it to our load case to start the structure stability analysis. So I can edit my load case number 1 just by clicking this Edit Load Case button, and then we see that if we have this stability add-on activated, we have an additional option here in the options, Calculate Critical Load Structure Stability Add-on. If we activate it, then we can here choose in the drop-down list our corresponding stability analysis setting that will be applied for our stability analysis. If I calculate now my load case number 1, then we will see in the calculation diagram that first the static analysis is performed of load case number 1, and that is used as a basis then for the stability analysis. When we have calculated our load case number 1, we will get the internal forces, support reactions for the static analysis, and we can also switch to the results of the stability analysis. In the navigator for the results, we have this drop-down list where we can switch between static analysis and stability analysis now. If we switch to a stability analysis, then we will see the graphical representation of the mode shape, and by default for the members, it's represented by those line display. We can also choose the display mode. Here in the navigator for the results, we have options at the bottom. So if I choose to display my deformations for the members by colored sections, then I will also get this colored representation with the sections. So that is mostly easier for the imagination of the mode shape. I also get the results in the tables. So in the result tables for stability analysis, I will now see my critical load factor corresponding to the first mode shape. For this example, the first critical load factor is at 33.6. So that means that if I multiply my load of my load case number 1 with 33.6, then I will have the stability failure with this mode shape of my simple frame. Okay, so that is the result that I get, and I also get further mode shapes according to my setting that I have set in the stability analysis settings. Now, I have said that this is only a 2D structure. So the first mode shape is this in-plane flexural buckling of the frame, and I don't get any out-of-plane buckling shapes. If I also want to consider the out-of-plane buckling, then I can go into my base data dialog and change the model type to 3D. I will do so. Okay. And then I can also just try to calculate it again. And then I will see I have not changed anything with my support conditions. So the result of the calculation in this 3D model environment now will be that there's an error because the structure is unstable. So for my easy structure, that is very easy to determine the cause because I have not changed my supports. So I have the simple supports here, but I don't have any support in the out-of-plane direction. So for this case, it would be easy to say, okay, there are supports missing. But also if you have more complex models and you get this error for instability, the structure stability add-on can also be helpful. So as I have said in the overview, there's another option. If we go into the stability analysis settings, we have this option for the calculation without loading for instability check by mode shape. So we can use this method if we think there may be an instability due to modeling issues, if maybe you have forgotten a support, or also if you have nonlinearities, you can use this option here. okay, to check if it's maybe a modeling problem that your structure is not stable, like it is, for example, in this case. And as a result, you will get the mode shape of the unstable structure, and then you can easily see what the problem is. So in my case, yeah, I don't have any support in the out of plane direction, so I will see that the frame will have a high deformation, and so there won't be any restraint, and it will not be a stable structure that can be calculated. So also this option is in the structure stability add-on that can help you in case of modeling issues with instability. In my case, it would be easy, so I just wanted to place some supports here. So I will have the supports in Y direction in the frame edges. Okay, so I select the Y direction here and assign it now to my frame edges. Okay, here and the other one. Okay, perfect. So now I can change the setting back so that I calculate my mode shapes with loading to get the corresponding buckling shapes. Okay, I will calculate it again, load case number 1. Now also in the 3D model environment. So now I would expect to get also out of plane buckling shapes. Okay, I switch to stability analysis results, and now I see that the first mode shape is no longer this in-plane buckling, but now we get also out of plane buckling for the beam and also for the columns. So for example, for this column, now I get this mode shape for out of plane flexural buckling with a critical load factor of 13. So the result of stability analysis add-on is not only the critical load factor and the mode shape, but we also get the calculation of critical loads and also of buckling length. So if we go into the result table, results by members, then we will also have additional tables like effective lengths and critical loads by member. So using this load amplifier, the stability add-on already automatically calculates critical loads for each member and then determines effective lengths and corresponding to the member length, also effective length factors. So if, for example, we want to look at the effective length of this column, so I click on it, it's member number 3, then we have to look also at results for mode shapes where this member is affected. So mode shape number 1, that would be for the beam, but mode shape number 2, that is the one for out of plane buckling of this column. So as it is out of plane buckling, it would be buckling around the weak axis. We can also display the axis system, so buckling around the z-axis, and the corresponding principal axis now would be the v-axis. So we have to look at member number 3, mode shape number 2, and L critical V. So it's an effective length of 6 meters, and the corresponding effective length factors would be 1.0. So that is as expected, as you would say the critical length for this column with hinged support conditions at start and end would be the member length. Okay, so this would be the effective length for the buckling around the weak axis, and buckling mode shape number 4, that is now still this in-plane flexural buckling, that would be for buckling around the strong axis. So member number 3, mode shape number 4, and now it's L critical for the U, around the U axis, around 16 meters, and this effective length factor of 2.6. So those values could now be used if we want to perform, for example, stability design checks according to the equivalent member method. Then we could also use this effective length factors for the further design. Okay, so we get from the stability analysis result mode shapes, critical load factors, and also effective lengths for the members. So I think that is good. We have seen all this input on this simple example. And now I want to also give you some hints about the behavior of the stability analysis add-on in a 3D model. So now I switch to my next model for this webinar. It's a steel hull with simple frames, so rigid frame edges, also simple supports, and asserting loading. I have simplified it a bit, so I only have self-weight and snow load, and then wind loads only one per direction, so I have not considered also the negative ones, for example. So it's a bit simplified, but I think for our example today, it's a good example. And now you can also calculate critical mode shapes with the stability add-on for this 3D structure with consideration of all the structural elements. So the whole structure is considered, and you don't need, for example, to consider any spring stiffnesses for members that are not considered, so like the bracings. So it's already considered in this 3D model with its corresponding stiffness. So we can have a look at it. First, for sure, we would need to activate the add-on in the base data dialog. So add-ons and structure stability. Okay. Now we also have the stability analysis settings in here, and we can assign it to our load case. So if we want to determine the critical mode shape, then we can, for example, select a load combination where we think that we have the most governing load, like for example, combination number 5, I would say. I can also activate this calculate critical load for the structural stability add-on and calculate it. So we can also assign this setting to load combinations and not only to load cases. So now, again, first static analysis of the load combination and then stability analysis using the internal forces that have been already calculated. So now we see, okay, the mode shape number 1 for the critical load factor of 18 in load combination number 5 is displayed here. So now that's only one load combination. For a structure where we have lots of load combinations, it would be interesting to find out the one who would be the governing one for the stability analysis. So the wish would be to analyze the stability of all the load combinations and not only of one load combination. So that is also possible. So we can go into the combination of the loadings, so design situations. And as you probably already know, all the rules for the combinations are set into this combination wizard. So we can also modify the combination wizard. And then there's an option for stability analysis. With the activation of this option, we can also activate the stability analysis for all our load combinations that are created by this combination wizard. So I will activate stability analysis, and I want to recreate my combinations. So I set it here again. They are recreated, and we see now every load combination will have this calculate critical load option activated. If I now calculate my design situation number 1, then I will get all the results of all the load combinations. So then all the combinations will be also calculated by stability analysis. In the results, I don't have to look then at each combination one by one, but I also get the results of the most critical load factor. So we will also look at this result, and we will see it in the result tables. So if I am in my design situation, in the summary of the static analysis, then I will also have this additional line of minimum critical load factor. So now we see the most governing one is my load combination number 6 with a critical load factor of 11.1. And then we can have a look at combination number 6 and the results for the stability analysis. And we will see that it's also this mode shape for in-plane flexural buckling. So that is the most critical stability issue for my load combinations that are present in my design situation number 1. Okay, if we look at this mode shape, we see it's in-plane flexural buckling. But when we look at the internal forces, then we also know that from our loading, so there's snow load, wind load, we also get a bending moment My. So we would also expect to have here a lateral torsional buckling problem of our main beam. So we haven't seen this mode shape now from the stability analysis. And the reason is that in our standard RFEM and RStab calculation, we only have this 6 degrees of freedom solver implemented. So also for the stability analysis, we can cover flexural buckling, but we don't get the mode shapes for lateral torsional buckling if we don't have this additional add-on activated for the 7 degrees of freedom. For a short overview about the possibilities, I want to show another page in the PowerPoint, okay. And we want to have a look at the stability failures of the members. So as we already know, we have this problem or stability issue of flexural buckling. So we have a compression force in the member, and then as a stability mode shape, we will get this lateral deformation. So there we have the critical loads and critical for buckling around the principal axis or around the geometrically axis, so strong and weak axis, the flexural buckling mode shape. But also there are other stability issues. So we also have the torsional buckling mode. So mainly it's an issue for such cruciform members, for example. So as a stability mode, we will get just the deformation around the longitudinal axis, so no lateral deformation. And then we also have another mode shape. It's a combination of both of the ones shown before. So we have flexural torsional buckling. So if I have a compression force and it's an unsymmetric cross-section, for example, then I will have this torsional deformation and also lateral deformation. So, and then we will get the critical compression force for it. But also for members in bending, we have this problem of lateral torsional buckling. So the compressed flange will get lateral deformation. And so for the whole cross-section, we have this torsional and lateral deformation. So this is the lateral torsional buckling. In steel design add-on, for sure, with the equivalent member method, we can calculate the design checks for all those failure modes. But if we want to consider it in the global analysis on the 3D model, then with the standard calculation, 6 degrees of freedom, it's only the flexural buckling shape. And if we also want to consider torsional buckling, flexural torsional buckling, and lateral torsional buckling, then we need this additional add-on for 7 degrees of freedom. So, and that leads us to our next topic, the torsional warping add-on, 7 degrees of freedom. So in general, we can use this add-on to consider the cross-section warping as an additional degree of freedom in the calculation of our member elements. We can use it also in combination with the structure stability add-on so that we also can determine critical load factors and mode shapes for the stability mode shapes like torsional buckling or lateral torsional buckling. The whole add-on is fully integrated in the programs RFEM and RStab. Possible applications and use cases of this add-on are listed on this page. So we can use it for all thin-walled cross-sections where we have intended high torsional moments, for example, craneway girders, where we want to consider the torsional load so that we have primary torsion and secondary torsion. And then it's also used, the 7 degrees of freedom add-on, for the calculation of lateral torsional buckling according to the standards for non-doubly symmetric cross-sections. So for example, for channel sections, we can't use the equivalent member method according to Eurocode 3. So we would need to consider the lateral torsional buckling problem by using second order analysis with 7 degrees of freedom and also consideration of imperfections. So we will also look at this problem of the lateral torsional buckling check later. And also we can use this add-on to consider it in the stability analysis of the global model so that the stiffness of all the connected structural elements is considered correctly. Okay, now I want to begin with a very simple example. So the example I want to show now is a craneway girder, which I want to model in RFEM 6, and I want to show all the necessary input for the application of this torsional warping add-on. So I just want to create a new file, and it would be this craneway girder, and I want to activate the add-on torsional warping. Maybe I will go back to the main tab, because you see I use now the model type 3D. If I want to use a 2D model type, for example, then I can't activate this torsional warping add-on, because if you want to consider the 7th degree of freedom, then it's already a 3-dimensional calculation method of the members. So we would need at least this 2D, 3D model type. or the 3D model type. So if you have only 2D, then you see torsional warping is not available. So now we use 3D model type, and then we can activate the torsional warping. And as I want to calculate a crane weight girder now, I also changed the load case classification for the crane race. Okay. So in this example, I don't want to deal with all the necessary design checks for the crane weight girders. So we don't have them implemented yet in RFEM 6. So no fatigue design checks, for example, and we also don't have this moving load situation. So that will be implemented later. But now I only want to show this example because then we can look at all the details for the calculation with the warping torsion add-on, because we will get this torsional moments inside our crane weight girder. Okay, it would be a very easy example for the beginning. So we will start also with an I-shaped section. I want to have an HEB 300. So I just select it from the library, and I use this search function at the bottom to have it only in my list, and then HEB 300. Okay, for the material, it should be an S235. So that is already okay with the default material for me. So I confirm the setting and create my member. I want to have it with 12 meters of length, so I can just pick the points of this line grid here. Okay, so that is my member, and now I want to place supports. So I want to have also a torsional restraint at the beginning. Okay, so all the deformations and also the rotational restraint around the x-axis. Okay, and also another support at the end. So it will be the same, but now I don't have this longitudinal deformation fixed. I also want to consider an additional support in the middle, so it should be a two-span beam. And now I use this function of dividing the member. So I right-click the member, then in the members I choose this divide member by intermediate nodes. I can select one intermediate node, and now I want to use this option, create on member nodes without dividing the member. So that is important for the warping torsion analysis, because only if the member is considered as one member without division, then also the torsional warping will be continuous in this member. So if I would divide the member, then those two members would be independent. We will later also look at this problem, and there are also solutions for that. But for now, I want to use this option to create only the nodes on member. Okay, so now I have this node on member, and I also want to have another support here. So I just copy this one also to the middle. Okay, so that is my beam and also the support conditions. And probably you have noticed that in the support conditions, even if we have activated 7 degrees of freedom, we only have this 6 degrees of freedom for the support conditions. So in our calculation, we only have this torsional warping degree of freedom for the members. So it is seen just as a member problem, and also as a member property, we would need to define warping restraints, for example. So the nodal supports, they could also be used on surfaces, for example. So we have decided not to offer the warping restraint as a nodal support, but as a member property, because it's also only valid for the members. And for this, we can edit the member, and then we have this transverse stiffeners. So this additional type is used to place transverse stiffeners for the design and also supports for the warping torsion analysis. So as it's like always in RFEM 6, we have this additional tab, and now we can create types of transverse stiffeners, which could then be assigned to the different members. So now we have this new type of transverse stiffener, and we can see as a stiffener type, we can select between different options. So we can place, for example, end plates at start at end, or also flat stiffeners, and also the warping restraint. So in my example, I just want to place a full warping restraint at the beginning and at the end, and that is possible using this warping restraint object. So there's the user-defined restraint also available, but I want to use the full warping restraint here. I set one at the position of 0 and then a second one at the end. So I use the relative input by clicking on this button, and at 100% of the beam length I will have the second full warping restraint. I also want to add a flat stiffener in the middle where I have my other support. So at 50% I have my flat stiffener with a certain material and thickness, so 20 millimeter, and also the width of 120 millimeters. You see that automatically the program calculates the resulting warp spring that will be used in the analysis. So from the input of the thickness and the width, we will get automatically with the cross-section properties the warping spring that will also be considered in the analysis. So you can use this type of member transverse stiffeners to set all the warping restraint conditions for your member. Okay, we also see a certain graphical representation. So this is the full warping restraint, and here we have our stiffener placed in the middle. Okay, so now we have our system, and we would need some loading. And in the load cases, we already have created this load case number 1 for the self-weight. And the self-weight is applied automatically by using this self-weight factor in the Z direction. By default, if we have switched to warping torsion analysis, all the loads are applied also in the center of gravity. So also the connection between all the adjoining members and the supports, they are assumed in the center of gravity. And also the loads by default are applied in center of gravity of the cross-section. So that is a difference compared to the standard 6 degrees of freedom calculation in RFEM. So there we always apply the loads in the shear center, but now for warping torsion calculation, this additional torsional moment is important. So now it's really applied in the center of gravity. So we have already our self-weight loading, and now I want to also create some crane loading on my beam. And as I have said, we don't have this moving load implemented for now. So I could create it, for example, by hand, and I will just first show it as an example. So for this craneway loading, I will use the member load for now, and I use the concentrated load distribution type. So not the uniform one, but the concentrated, and I want to have 2 loads. So I think this load application would be appropriated here. So I have 80 kilonewton of vertical load in this example with a certain distance, 3.5 meters, for example. And the important thing now for the calculation with warping torsion is also the eccentricity. So for stability analysis and also for static analysis, we need to apply this eccentricity correctly. And if it's a craneway girder, I want to also assume a railway on the top. So I have a certain force eccentricity, in my example, of 180 millimeters. If it's just a simple case like top flange or bottom flange, then I could also use this simple reference points. So the middle one is the center of gravity, and then we have the upper left edge, for example, or the lower center point. So we can also directly apply it using this reference point, for example. But as I have an additional eccentricity, I just type it in here for this just as a value. A negative because the local z-axis is going downwards. Okay, I can just apply this load at the member number 1. And I could also apply another one, for example, a horizontal load. So just one load with 20 kilonewton at the same load distance, now in the y direction, still with the same eccentricity. Okay, so I apply it to my member. So I can create the load manually like this. So now I would need to copy the load cases because I want to have it moving, and then also change the distances for the first loading point and the second loading point. So that would be possible, but yeah, it's quite a bit of work. So I want to use another possibility here. You have probably seen in the previous webinars that now in RFEM 6 it's always possible to use JavaScript code for the creation of the model. So if you activate the script manager, we have it here in the list, the script manager, you will also get example scripts for this creation. So for example, in the examples, we have a simple beam one. If I just open it with the text editor, then we will see that there are also examples for creation of materials, how to create a node or a member, and for our case now, the important thing for the creation of a concentrated member load. So you see we can create this member load by JavaScript code, also set this load distribution as concentrated, the direction, for example, and a certain load magnitude. So basically all the options we have in RFEM, they are also available in the scripts. You can see all the options if you also open the console. So we have it here with a small info button. And if we click on it, we will see all the objects and all its properties. So in our case, for example, it's a load case. And we have also member loads inside. So it is here. And then you see we have all these options available. So all the distances, also eccentricities, and you see how you can apply it in the code. So that is always good if you need to find a certain property and about how to set it. And then it's relatively easy to create this JavaScript. So from this simple beam, I have created another one for my simplified craneway loading here. So I have certain input data with a distance between it. And then I set my concentrated load for the horizontal load with my eccentricity of 180 millimeters. And then also this concentrated load in vertical direction, as I have done manually, but now it can be done by JavaScript. So then I have this for loop that it creates automatically the load cases and the loads in each load case. So I think that is a very easy method, and it's not too complicated with this simple code snippet. And to apply it, you can just copy it here into this console. So just copy it and paste it. And then before applying it, I want to delete this load case number 2 again, because it will be created by the script. Okay, and with the return key, I can just start the script. And now you see in my load case list, I have created those additional load cases with my member loads. And if I click through them, you see it's this moving load, which I have simplified, applied by this JavaScript code. So that's also an easy solution. If you have things that you want to automate, which are not implemented by default in RFEM, you can also use JavaScript to create the objects. Okay, now I have my load cases, and I want to change the action category for them. So it's from the cranes, and they are alternative loading. So I will just change this action type to alternatively. Then we have our design situations and the combination rules. I think you already know that from previous webinars, like the steel design one. So in this example, I don't want to show it in detail, and I also don't want to look at the design situations for the deformations, but just for the ultimate limit state. Okay, now I have created my load combinations. So for each load step, I will have this this combination. If I now calculate this design situation, I will get the results for my load combinations with the warping torsion analysis activated. So we will have a look at the results. And now we also expect to get the torsional moments correctly. So primary torsion, secondary torsion, we will get it here in the result navigator. In the internal forces, you will see we have this additional choices. So the beam moment, for example, and also primary torsion, secondary torsion. And if we look now, for example, at a certain load combination, like this one, we have here our eccentric load, and so we have here this change in the secondary torsion because this load is applied. Also the warping deformation, we will get it as a result in the local deformations. Okay, so now we have calculated our load cases, and that could be used now for the steel design, for the cross-section design, without the stability analysis. If we now also want to perform our stability analysis, so in this case it would be a lateral torsional buckling check, we want to consider also the torsion correctly, so we would need this add-on with 7 degrees of freedom, a calculation according to second order theory, and also the imperfections. So that would be then our lateral torsional buckling check. So in this case, I want to create the imperfections from the stability add-on. So I want to use the mode shape and scale it to the certain value that I can easily create my imperfection. So we'll close this script manager again. Okay, and now activate also the stability analysis add-on. So now in the add-ons, structure stability. Okay. And now I could also analyze all my load combinations, for example, look at all the mode shapes and scale them to a certain imperfection value. But in my example, it would be easier to create this imperfection out of a mode shape, for example, of my self-weight load case, because then I would have this symmetric mode shape which I would need for my imperfection value. So in this example, I just want to apply it for this self-weight. So I activate this option, calculate critical load, and then calculate my load case number 1. And as we have now activated the torsional warping add-on, we now also expect a lateral torsional buckling shape. So not only flexural buckling, but we will see it here if I activate the deformation by colored sections. Okay, and then we see now with the 7 degrees of freedom add-on, we get this lateral torsional buckling shape. And now I want to use this one to apply it as an imperfection. For that, I can go into my navigator data and create a new imperfection case. So in this imperfection, I right-click the imperfection case to create a new one. And if we have the stability analysis add-on activated, we also have the imperfection type of the buckling mode that we can use. If I create imperfections from a buckling mode, I first have to select the load case. So in my example, it's load case number 1 and also buckling mode number 1. And now I need to set the imperfection magnitude. So for our lateral torsional buckling design check, the standards are giving also imperfection values. So in the Eurocode 3, you will also get imperfection values for flexural buckling and also for lateral torsional buckling. And now you could also apply this imperfection. So in my example, as an imperfection value, I can use 1/200 of the reference length, which would be between the fork supports in this example. So this length and 1/200 of this length will be the imperfection value that I would need to use here. It also depends on the national annex for the Eurocode. So it's always important to look at the national annex of your country so that you can set the correct imperfection magnitude. So if I want to set it here, I choose the imperfection direction in the Y direction, and then I could manually calculate the imperfection magnitude, or again, I could use the formula input, and also in these formulas, the JavaScript code is allowed. So now I can also get the properties of all the RFEM objects. So for example, from my members, it's member number 1. I can also get the length information here. So it was 12 meters. And now I want half of it because the support is in the middle, and 1/200. And so this imperfection magnitude would be the value that I should use. Okay, and if I now change the member length, for example, also this value would change because it's defined by the formula. Okay, in my example, I would also need to check the imperfection in the positive or in the negative direction. So depending on the load case which I analyze. And as I want to analyze all my load combinations, I want to also set this imperfection in a negative direction. So that can also be easily done using this group of imperfection cases. So this imperfection type can be used, for example, to combine different types of imperfections. So if I, for example, have a global initial sway imperfection in the x direction and then want to combine it together with local imperfections like the one I have from a buckling shape, then I can do so in this group of imperfection cases just by adding additional lines and setting a certain operator. But in this case, I just want to use it for applying my imperfection case number 1, but with factor -1 so that it's just in a negative direction. Okay. I can also display the shapes of the imperfection cases. So if I just calculate this imperfection case number 2, then it takes the mode shape of load case number 1, scales it to the value, and as we have the negative factor, we will have it in a negative direction. And then we can look at the results for the global deformations. So this is my imperfection shape now in imperfection case number 1 and in imperfection case number, sorry, it was in imperfection case number 2. And now I can also calculate it for number 1. And you see it's just the opposite direction with the imperfection magnitude that I have set in the imperfection case. So imperfection case 1 and 2. I can now use the imperfection in the combination. So in my design situation number 1, if I look at the combination rules, so in the combination wizard, I can here activate my imperfection cases, and then they are also considered in the combination. So if you look at the load combinations, we see now we have the same loading one time with imperfection case number 1 and then imperfection case number 2 and all the load cases. So and now if I calculate this design situation number 1, then I will get the internal forces calculated by second order theory with the imperfections and also the warping add-on activated. So I could use this internal forces in a cross-section design check, and that will replace my stability design check for lateral torsional buckling. So that is possible according to Eurocode 3, and then I could use those internal forces. So all the internal forces I get now in this design situation number 1 can then be used also, for example, in stress-strain analysis add-on or also in the steel design add-on. So I want to show that before. So if I just activate my steel design add-on in the base data dialog, so maybe it's also a good idea to just save the structure. So okay, I just saved it. And then I activate my steel design add-on, and I can look also in the input tables. I think you already know this input from the steel design webinar. So we have our design situation where all our internal forces are considered, then objects to design, materials and sections. That is automatically overtaken from the RFEM definition. And the important thing now for our cross-section design check, if you want to use it as stability design, we need to look at the ultimate configuration. So if we go inside here, then we can activate this option. So we want to perform the stability analysis with the second order internal forces. So we would now need this partial safety factor also for stability design. So normally the cross-section design checks are performed with the partial safety factor gamma M0, so for cross-section design checks. But for stability design checks, we would need the gamma M1 partial safety factor. So depending on the national annex, this factor can be different. So we need to activate this option. And also we don't need any other stability design checks, so no need to perform the equivalent member method again, because we already have all the effects in the internal forces. Okay, so now this setting is applied to our member. I see that the add-on is deactivated again, so I will activate it, steel design, but I think all the settings has been made. Yes, okay, so this is the correct setting with this gamma M1 factor. And now I can also calculate my steel design. And then I will see all the steel design checks with consideration of all the internal forces, including beam moment, secondary and primary torsion. So if you look briefly in one of the design checks, so for example, the most governing one here, then we see in the results, we are doing this, we are calculating the equivalent stress, considering the stress from bending moment about strong axis, weak axis, and also the axial stress from the warping beam moment. So all the necessary internal forces are included, and then we also use now this gamma M1 factor for our cross-section design check, because it's meant as replacement for the stability design. Okay, so I think we have seen now how to consider the 7th degree of freedom on this simple example and what we would need as an input. And now I think we can look again at our 3D model. So I will switch back to the steel hull that we had before. And now we also want to check the lateral torsional buckling on this global model. So for the beam girders, we would now also expect to get this lateral torsional buckling shapes. So first we need to activate the structure stability add-on. We have it already, and also the torsional warping add-on. Okay. And now I just want to give you some additional hints, because if we look at this model, as we have said, all the members are by default independently for the warping. So all the members are free at their edges for warping. And now we still want to see these beams as a continuous one, so that the warping can be continuous in the whole beam. Therefore, we would need to create member sets. So that is the option if you have members which are not connected. So if you don't have this internal nodes, but real nodes, then you can still consider them for a continuous warping if you create member sets. So I will create the member sets. For that, I will activate my visibilities for the members to only get the beam ones. Okay, so then I can select all the frames easily, and I don't want to have this additional columns here. Oh, so this one. Okay, and I just right-click on the members, and I can here create the member sets. It automatically recognizes that I have independent systems here, and it tries to create the continuous member sets. So you see, I can now easily create the member set for all the frames. Okay, so that is possible now to consider those members also continuous in the warping, because that is the property of the member set object. If you don't want to have it continuous in the warping torsion analysis, then you could also activate this discontinuous torsional warping. But normally when you create a member set, it is meant to have it as one structural object. So you will have continuous warping for all the members which are connected in one member set. Okay, so that is the first important thing, that we can consider this beam as continuous one. And then we already also know that the load application point needs to be defined by the force eccentricity. So in this example, I just want to change the force eccentricity for this no load. So I want to also apply it at the top flange. So for the 6 degrees of freedom calculation, it was not necessary, but now if I want to consider it in the warping torsion analysis, I also want to consider this eccentricity in the stability analysis. So I just added my member loads and set this eccentricity value here. In this case, I can use the simple reference point, because I just want to apply it at the top flange of the cross section for all this members. So I can use this simple reference point. Okay, so now I have changed those two settings, and I want to run now the stability analysis. I think we still have it activated from the example before. So if I calculate my design situation number 1, I have my 10 load combinations, static analysis, and then stability analysis. And now I would expect to also get this lateral torsional buckling shapes. So before, it was only the in-plane flexural buckling, you probably remember. And now I want to look at the most governing mode shape, which would be lateral torsional buckling. So if we look now at our design situation number 1, the minimum critical load factor now is not 11, but now it's 1.4. So if we look now in load combination number 6, in the results for the stability analysis, then we see that now the first mode shape is also correctly found as this lateral torsional buckling shape. And automatically, as we are working now in a 3D model, also the stiffness of all adjoining elements is considered. So already the bracings and all the couplings between the members, that is correctly considered. And so we get this critical load factor. So we can also do detailed stability analysis on a 3D model. So for example, to consider also the coupling between beams that are not equally loaded, for example, to also consider the stabilizing effect. You can also see that the structure is considered, for example, if in this example I changed the section of the bracing from a round section with 20 millimeters of diameter to one with only 10 millimeters. So in this example, I will just rerun the stability analysis now with bracing that has a lower stiffness, just that you can see what we will get as a result. So in this load combination number 6, before it was this lateral torsional buckling between the fixation of the bracing. But now we have a lower stiffness, and now it's not stiff enough to prevent this this flexural buckling of all the frames. So now we have a lateral torsional buckling mode shape with critical load factor 1.1. So the first one is now the most critical one with this lateral torsional buckling mode shapes, not between the bracing fixation, because the stiffness is too low now. So we will have this global lateral torsional buckling here. So you can see that this stiffness is directly considered of all the adjoining elements, and there's no need to calculate a certain equivalent spring stiffness, for example, in this 3D analysis. So you can use this combination stability as a structural stability add-on and torsional warping add-on also to perform detailed stability analysis on 3D models with member elements. Okay, so I think that were the examples that I wanted to present you and the two add-on models. Now I can give back to Andreas.
Thank you, Oliver, for this nice presentation. I would like to show the attendees your the website with the knowledge base article about the torsional warping. Just a moment. Yeah, on dlubal.com you can find our knowledge base, and with the articles, a lot of valuable articles. Just use them, they are for free for you. I search for warping, and then the article should be displayed. Here above, lateral torsional buckling analysis with new torsional warping add-on. Just click on it, and that's the full article. It could help you for your project if necessary. Okay, then you can download our free trial version. It's valid for 90 days, and you can try RSTAB 9, RFEM 6, and so on, the other programs. RFEM 6 and RSTAB 9 contain all the add-ons, for example, the torsional warping add-on and so on. Okay, just try it for free. So at last I would like to show you the webinar today, news and events webinars, where you can find the recording. I have to scroll down a little bit. Yeah, that's today's webinar. The recording will be here in the next days, and you will find the presentation slides, the script file, and the models. But you will get an email maybe next week with your attendee certificate, and you will get the information about the recording, that it is online. Okay, that's also all from my side. I would like to say thank you for your attention. Thanks to Oliver for this presentation. Thanks to Sonja von Bloor for answering the questions. I wish you all a nice rest of the day. Stay healthy and bye-bye.